Work, kinetic energy, and potential energy, and introduction. Here we go. Is this guy doing work?
Yep.
Why do you say that?
Because it's moving.
Is he applying a force?
Yep.
He's applying a force, and there's a distance, right? Ooh, there's even a shadow there. That's kind of cool.
Ooh, detail.
Okay, so the nature of work. In the everyday sense, work involves pushing, pulling, lifting. There has to be some movement, right? Work is the measure of the amount of energy that is transferred. Now that, my friends, is key. Energy must be transferred. There has to be a transfer of energy. When a certain force acts through, that should be not as, a certain distance. To do a job. Energy, oh there it is there. Energy is transferred when work is done. That's the key thing, right? If you have to write one thing down on that slide, that's what you should write down. That's the only thing that's important. Please don't write the whole thing. Energy must be transferred. In fact, if you can remember that energy must be transferred, he repeats it for the third or fourth time, hoping they'll remember. You probably don't need to write it down at all. Okay, so let's say we've got a horizontal force. A horizontal force applied to a dynamics cart, one of those cart thingies that I play with. For a certain distance, work is done. Energy is transferred to the cart. Why is energy transferred when I push it? Or how does it show up as a transfer of energy? I use my regular human strength. Push the cart, and it, well, it does what? Speeds up. Yeah, I need a tracker, right? Scratch them in the head as I go by. Hey. Okay, Johnny?
Yep.
Alright. I apply force, and it, now it has what? In the form of movement. Now, you will notice,
Slower.
if I planned that better, I would, I would have amazed you more, right, if I'd done that.
Yeah.
I pushed it, and it has what kind of energy? Kinetic energy, because it's moving, but then it slowed down. So where did the energy go? Because energy must be conserved. The transfer for there to be work, but energy must be conserved, right? Sorry, we're taking heat, you're right. The energy got transformed into heat by friction. Friction, right? Now, there might also be, there's not a lot of friction here, so it's quite likely this ramp, this track is not perfectly flat, and it's actually down like this. So where did that energy go? Let's just make this steeper.
What's the name? Yeah.
Grab the, it's going to fall off there. No, just, grab it. What if I do this? It obviously had kinetic energy. Was work done on it?
Yeah.
I'm actually asking questions here because I'm not sure where this is leading. Can you tell the difference that I don't know what I'm talking about? Can you really?
No.
So I always sound like I don't know what I'm talking about?
No, you already started. I don't know.
Sometimes you sound unsure. Like, kind of sound
I am unsure because I've got a question in my head and I'm afraid to ask it because I don't know the answer.
So ask it. We can figure it out together.
You're right. Yeah, absolutely. I'm always, with grade 12, I'm not so worried about asking questions that I don't know the answer. Grade 9 don't like that.
Why?
Because teachers have to know everything according to grade 9. You remember.
No,
Okay, so if I let go, it gets kinetic energy. Where does the energy come from? Gravity.
it comes from.
Well, it's gravity that's pulling it, but where does the, I mean, when I do this, when I lift it up and put it here and have potential energy, I gave it the energy, right? I guess I did. I pushed it there. Yeah, that's true. Maybe, okay, so I put it there. I gave it the energy. But if I do, no, I guess I would say a bit faster. That's how. So there is a transfer of energy. It just was delayed. Okay, that's right. It's no different than me doing this and then letting it go, right? That's right. That's the same thing. Yeah, because what I'm doing is, like if I put it down, and then I lift it, it has potential energy now, right? So if I drop it, it's going to fall, right? And likewise, if I lift it up and then I place it there, I've given it energy that is then released by.
Yeah. That's cool.
Now I do know what I'm doing. Hooray for me.
And now we know.
Work is done, energy is transferred to the cart now has kinetic energy. Someone said that before. Okay, so again, it's that transfer of energy idea. Note that when a force applied at an angle, cart moves horizontally. The only force which does useful work on the cart is the FAX, the horizontal component, right? Because how come? Because that's the direction of the movement, right? So the force and the movement have to be in the same. The amount of force that is in the direction of movement is the force that's causing the work. So you could expend some energy here, some energy that is not converted to work. Does that kind of make sense?
Yes.
Okay, so here's a guy in a brown uniform, maybe works for UPS or something, lifting an object or a box. When an object lifted, work is done. Through a certain distance, a certain force is exerted through a certain distance. Energy is used up or transferred to get the job done. But the kinetic energy of the bricks is zero. Where did the energy go? I've already alluded to this already. You guys already know. Where does the energy go? It's been transformed into potential energy. Right? As I lift something, it's got potential energy because if you let it go, it could fall. Then potential energy gets converted to
So if it
kinetic
hits
energy.
the ground, then the potential energy goes into the ground.
Well, when it hits the ground, let me find something that I can drop easily. Something that won't break today.
Where does the energy
If I lift this up, right, it's got potential energy. I let go, it has kinetic energy. So when it hits the floor, where does the energy go?
Does it just turn into E?
It does, actually. If you've ever played, does it make sense?
No, how can it, like, it just fell, how can it have heat?
Well, it's got heat to the lens. Have you ever played tennis, Todd?
Yes.
Or squash? Or actually the best... One night. The best example is actually racquetball. Have you ever played racquetball? We used to play racquetball in university. Actually, I had lunch with my buddy that I used to play racquetball with. We had a house together, there was three of us, and we used to go to racquetball court and we would play. Loser had to do dishes.
Oh, you told us.
Yeah, you
That's how
told
it
us
is.
that.
That's very intense. But anyways, if you play... Pardon me? Oh, there was a lot of dishes.
I did do dishes until save up the money.
Actually, can I give you a university hint?
Yes.
Yeah, you're welcome. Okay, let's talk about potential energy. It's energy that's stored in an object because of its condition or position. Now notice that I say condition or position because when we say potential energy, most kids usually think of like an elevated position, but it could also mean like in a battery, right? That has potential energy, it's potential chemical energy. In food, there's potential chemical energy there as well. Okay? It's got to do with the electrons and where they are in their shells and stuff like that. But basically it's an elevated position of some type, usually. Okay? So potential energy. Energy that's stored in an object. Because I never did finish the story about the racquetball, did I? Sure. If you play racquetball or tennis, after you play for a while, you'll realize that the ball is much, much softer. How come?
Because it's all heated up.
Because it's all heated up. So, yeah. Racquetball for sure. If you take a racquetball that's fresh out of the can and one that's been played with in the last, like right away, way easier to squeeze the one that's been played. It's just much looser. It's warmer.
Is that why they use so many tennis balls?
Yeah, and they do tend to sort of get rubbed off, and yeah, they want them pristine.
They're just like, no.
Okay, let's talk about springs. When we stretch out or push in a spring, we do work on it. We transfer energy to it. We say that this work goes towards increasing the potential energy of the spring, and that would be a spring energy, right? There's the kind of springs where you can push, there's the kind you can pull, there's the kind that do both, but any of them will store energy. Can you think of an example of a spring that might store energy? In the old days, before you had watches with batteries, you had to actually wind your watch every day.
Every day.
Every day. You would wind it, it would store the energy in the spring, then it would use it after 24 hours and keep time. And if you
So
didn't
how long
wind
do you
it,
have to wind it for?
30 seconds? 20 seconds?
Wait, so how would you set your time, or would you have to set your time?
If your if your watch ran down, you would have to reset it to what the time is. And then, yeah.
Okay.
Yeah, you could. People, it was just kind of a habit, right? You sit around, you just,
Like,
and when you would get to the end, and it would get tight, and then that would get tight. It's so weird that I'm having this conversation. Nobody here has ever wound a watch.
Nope.
Makes me feel old.
it's okay, Mr.
I know how to watch, I had to do it, but I never.
Oh, yeah?
Oh.
Alright, that's not recycling. That's recycling.
Oh, but
I was the recycling one.
That's right, I remember that.
That was funny.
In general, anytime work is done, energy is transferred to an object and increases out of its kinetic or potential energy. I think I've been reading this. Right, I need to move on. Okay. So work is, now do you guys know what this funny symbol is here? Do
Infinity.
you remember?
Like,
It's not infinity,
explodes out.
proportional, which is more or less the same, Jerry. Work is proportional to the applied force. Work is proportional to the distance moved. Work is not related to time. Whether you do a job fast or slow makes no difference. You didn't hear that from me. It still takes the same amount of energy because it's the same job. So whether I'm lifting the tennis ball really quick or really slow, it's the same amount of energy. Now, having said that, how come if I do it really, really fast, I start to sweat? Or what if I run up what if I've got like a huge hill and I run up, when I get to the top, I'm sweating, I'm hot, I've expended more energy than if I just walk up the hill. So what's the deal with that?
oh no, less time.
Well, because it is less time, so it's more power, but you're also moving you're expending more heat more rapidly. So you can burn more energy by doing it fast. Okay, so that's sort of it's a bit of a misnomer. Anyways, we are leading towards work is equal to KFD, right? Or sorry, I guess I should say work is proportional to F times D, which means that work is equal to KFD. How do we go from proportion? Don't worry, I can see you guys now worrying.
Can we write that down?
No.
No?
What does the K mean? The K is the constant of proportionality. Every time, remember we did this when we did the circular motion thing?
Yeah.
Right? When you go from a proportionality relationship to an equation, you need some number, some K value that makes it work.
Oh.
Okay? Now, the K value here, and I'll explain this, don't worry. The unit for work is the Newton meter. Oh yeah, it usually should have something here. Okay, so 1 joule, work is measured in joules, and it's a Newton times a meter. So what we've done, because joules is a made-up thing, right? Like work is a made-up thing, it's a man-made, human-made sort of idea. It's not like circumference of a circle, right? We can define 1 Newton meter as 1 joule. So in other words, my K value is simply equal to 1. Okay, we define 1 Newton meter to be 1 joule, and then the K disappears, or it becomes 1. You don't really need to know. Some people might find it interesting.
So we could technically either put Newton meter or joule.
You could, yes. The Newton meter is equivalent to the joule.
Okay.
Not newtons per meter,
Newton.
Newton time meters. Newtons times meters. The basic unit is the Newton meter, which we call the joule. There's, what's his name? No, that's Joule. James Joule? Maybe James.
Jared Jewell.
He put a lot of energy into not shaving. What'd you say?
What?
Who? Huh?
Jared Jewell? I don't know.
Oh. 1 joule is the amount of work done when a force of 1 Newton acts through a distance of 1 meter. This conveniently eliminates the K in the equation. So there's the formula, and that's why Danielle was kind of confused a bit, because yesterday I said that's the formula, right?
Do we have it?
Work,
We'll put that down.
W equals F times D. W is work, measured in joules. F is force, measured in newtons. D is distance, measured in meters. Must be meters.
No one's there.
Must be meters. If it's given to you in kilometers, you got to convert. Oh, that's it? Whew. Oh, there's more. There's got to be more.
Rest time.
No rest. Okay. Do you have, did I give you these? I gave you the sample questions? Excellent. I think they did, right?
Sample problems work.
Sample problems work? Okay. Let's do a couple of these, and then I'll let you. Okay. So let's do it. Now, do you get the feeling that these questions are going to be easy?
No.
Really? Because they are.
Because they're going to get very complicated.
Well, it can be a little bit, but these introductory ones are super easy. How much work is done when sliding a 30-kilogram chair a distance of 15 meters across a rough surface where the force of friction is 50 newtons? Now, it doesn't say it in the question, but it doesn't say anything about acceleration, so you can assume that this is at a
Constant motion.
constant velocity. It doesn't come right out and say it, but okay. So if the force of friction is minus 50, then that must mean that I have an applied force of 50 newtons, right?
Yes.
Does the mass of the chair matter?
Yeah.
Probably not. Yeah, I think
If it's
it
there, it matters.
Why do you say that, Daniel?
It always makes sense.
Always matters?
Because if it's heavier, it should say it's more work.
Well, that's true. Yeah.
Like,
But,
the heavier weight is, the more work.
like, for example, if I'm pushing this table, it requires a certain amount of force, but if one of you guys sat on here,
It would be more.
see a whole lot more work, right? Why would it be more work?
Because it's more.
Because there's more friction. So the mass has already been factored into the 50 newtons, right?
Whoa.
Like if this was, say, 60, well then that 50 newtons wouldn't be 50 anymore, it'd probably be maybe 75 or something.
Yeah.
So yes, the mass matters, but you know what? We're not going to use it. How much work is done?
Oh.
Work equals FD, 50 newtons of force, 15 meters, little mental math.
Wait, so if, like, later on with trickery or questions,
What trickery am I going to come up with?
I mean, we wouldn't have that 50 newtons, we'd have to use the kg.
If I gave you the, now actually, I should say this about the exam. Because I've said I will try to cover every question that you've encountered on the test, there will be some exam questions that cover more than one thing. Okay? Meaning I will combine questions together.
Oh.
Can you give an example?
Yes, like for example here, I might say here, Riley asked a little bit about this, right? I might say, instead of giving you the force of friction, I might give you mu, right? And then you got to do like a mu question, and then it goes into work. Or I might say that the applied force is greater than the friction force, and like how far does it go in X amount of time?
That'll,
But it would cover more than one question, right? Because then I can use it on here, and I can use it on this test too. I'm condensing the exam.
I'll, like,
Oh yeah, well, like those kind of questions.
why don't you just write it down right there?
They're probably going to be, we're good for time. Yeah, well, and to make it less questions on the test, yes. On the exam. Okay, so anyways, 50 times 15, mental math, 50 times 10 is 500, 50 times 5 is 250, add them together, 750 joules. Am I right?
Yes, you're right.
No.
Are we gonna?
Joules. We're going to go with joules. Everybody good?
See, we almost make that bank shot.
750? Dawson's got a concern?
Boston.
Okay, what about work done against gravity? How much work is done in lifting 2 bricks, each of mass 1.4 kilograms, from the floor to the top of your table, a distance of 80 centimeters? Oh, alarm bell should be ringing in your head. 80 centimeters, change it to meters.
Changed it.
0.8 meters. And there's 2 bricks. Now here's a trick that some people like to write. Instead of the number 2, they like to do that. And the kids read over it and miss it. So watch out for that, right? Like they write out the word.
Jimmy, too.
So how much work is done? We're going to lift these up. So now our force that's required is the force to oppose gravity. So we're going to have to go m times g. So that's 2 bricks times a mass of 1.4 times minus 9.8, I guess, really. It's not squared. 8 times 9.8. It's going to give me minus 27.44. That's the weight force. Therefore, the applied force would have to be? Yeah, the opposite, positive. Yeah, I think Mr. Cherepak has them, if you're looking for them, Kristen. Meters? Oh, meter sticks. Got lots of those.
Oh, there goes one.
Yeah, exactly. I have to remember to change these Okay, the force is 27.44. How much work is done? W equals FD. That's a preliminary step. I don't think we need to worry about it. It would be newtons, right? Well, it's 27.44, and the distance 0.8. I get 21.95. Let's say, well, I guess that'd be 22, right? Let's say 21.95 joules, right? These are pretty easy, aren't they? These are multiple choice kind of questions. If only. Oh, come on.
They required 2 steps, which technically means it should be worth 2 marks. Unless it is 2 marks.
Oh no, you didn't. I don't know. I get tricked up by those multiple questions. Yeah, multiple choice. Because I think they're supposed to be easy.
Where did you come
You end up
from?
having like high for some reason.
Oh, but the first one would be right.
A 1.5 kilogram dynamics cart pulled at an angle of 30 degrees above the horizontal with a force of 25 newtons. The cart moves 4 meters. How much work is done on the cart? Do you guys want to try this one?
No.
So interesting how some people, yes, they want to try it on their own. Others like, no way, I don't want to try that at all. You want to try it, Danielle?
I'm not ready.
Okay, but we won't ready.
90% of the class
All the more reason to practice it.
We should have took the exam before the break, but I'm lost.
Haven't you noticed how I'm kind of easing you in?
Yeah.
Okay, let's see what we got here. We got a mass. We got an angle of 30 degrees.
Mr. Bennett, this is like not related to this at all. But on the exam, can you put like a bracket in between the 3 and like the A? Like if it's
Yeah.
example 3.
So it's not 3A, because then I think it's 3A, but wait, 1.5. There's a period though. Period means end.
No. Example.
If you guys look on your sheet, it just says 3.
Oh, does it?
Mine says 3.
I have been caught before where it's like question 3, and then it's like 15, and kids have said, oh, is that 3.15? That has happened to me before.
Like even if we could get back to
If you're not sure, just ask. That's a question I'm quite happy to answer on an exam. Okay, we got an applied force of 25. The cart moves a distance of 4 meters. How much work is done? Work is F times D. We got the D. It's 4. The applied force is 25, but we have an angle here, right? So what's my step? Yes, I'm going to have to find the FAX, right? Going to have to find the FAX. So, FAX is FA cos theta. So that's 25 times the cosine of 30.
Seems bad.
Why are sine, cos, and tan are all over the place in this calculator? It's stupid.
Want to use mine?
21.7. 21.7 newtons. Now I'm going to go W equals FD. I guess that would be technically FAXD, I guess, right? If you want. 21.7. I'm very pleased how I can throw that at you guys, and you guys are good with that, because there was a time when some of you, or even former students, would freak out, oh, that's a brand new formula. Right? So I'm very pleased that you can deal with that now.
It's a brand new formula.
Really?
It's like other purposes.
86.6 joules, right?
Oh my god.
You know what? This unit is almost a review of everything else.
Yeah, let's just do this test.
All these vectors. The only thing that it doesn't really do is circular stuff, really.
Well, why don't we just do this test, like, put this test on the exam and then just do circular stuff?
Do you want to try this one on your own?
Yeah, we can do it. I'm ready to go.
Okay, I'll just do it. We got an inclined plane situation. We're looking for the amount of work to pull the cart up the plane, the amount of work done lifting the cart straight up, and the amount of work done if there's a friction force of 50 newtons up the plane. Okay, so we're going to push this 30 kilogram cart up this ramp. How hard, what's my FA? How hard do I have to push?
Get out your phone.
You can't? Yeah.
Do it.
Okay, how hard do I have to push? Do I know?
These are are they?
No, this isn't probably not. It doesn't say anything in part A. It would normally be the amount of friction, but here, is there an FD value?
No.
It's not given, but does it exist?
Yes.
Absolutely it exists, right? There is a force of gravity that's acting down the plane. And what is that FD? Little review here. FD is equal to mg sine theta. Remember that one? Isn't this great how we're doing this little exam review sort of here? 30 times 9.8 times the sine of 30 147.
Yep.
So the FD is 147. Therefore, the FA has to be also 147, right? I guess technically this is negative, if negative means down and positive means up the plane.
Big quotation.
Right? So if my FA is 147, then the work done is going to be FD, or FAD, I guess. $147 times the ramp is 6 meters long. 882 joules.
Oh, work.
That, yeah. How much work would be done? What if instead of pushing it up the ramp, what if I just took this 30 kilogram thing and just lifted it straight up there? Like, it would be way less work, would it not? Because we're only going 3 meters instead of 6.
Same amount of energy.
Because you're going to
With it?
there, and that one.
That's what you said.
That is what I said. Can we prove it, Talia?
I don't know.
Well, the
Of course
answer
we
is
can.
yes. Of course we can. Do the math.
Oh, that's a question.
That's B. The force is going to be, if I'm lifting it straight up, I'm lifting it against gravity. So my mass is 30 times 9.8.
Oh, John.
294. Is that one what? It is, I guess. But that means then that the applied force is positive 294, and the work is F times D, 294. Distance is half, 3. 294 times 3 what do you know?
So if you do that on the
Go ahead, and you could explain why. The amount of energy is the same. How come? Tanya is 100% right. It's not just because I said it. Because the potential energy at the top of the ramp is 882, and it doesn't matter how you got there.
It's always the same.
Right? Now, how come, like, here I only have to push it 147, but I have to push it 147 for a longer period of time. So if you are pushing, if you need to raise something, you can push it up a ramp. It's easier to push,
So you'd be more
less force. You just have to do it for a longer period of time, which is the whole idea behind ramps,
That takes half the time.
right? Like if you're in a wheelchair and you have to go up a flight of stairs, right?
It'd take you longer to get up those.
You could, I guess you could come up with some kind of system where you're pulling on a rope or someone could carry you, but the force would be tremendous. Or you can do it on a ramp where you have to do it much less force, but you got to do it a whole lot longer. Or in an elevator. Okay?
No,
Now there are, when you're talking about ramps, there are, when it comes to wheelchairs, there's minimum code. Like the ramp can be at a certain angle because they know what the average person, how hard the average person can push. So the angle has to be within a certain sort of boundary so that it's that easy.
90.
Yeah, you can't have like an 80-degree ramp. That's called a wall. Now, what if there is friction on the plane? Because there's almost always friction, right?
Okay.
So in part C,
Just like,
in part C, you've got your FD, but you've also got friction, right? So really, the applied force when you're going up a ramp with friction is going to be really equal to the FD plus the FF, right? So that's going to be 147
do we already know this?
plus is it 50 newtons? Yeah. Right? Yeah. So you would really need, if there was friction, you would really need 197 joules. Not joules, 197 newtons. You'd need more force. And I'm leading into something here.
Take that quick.
197, it's 6. So are you going to have to do more work if there's friction on the ramp? How can that be? You have to overcome friction, but how can the wheelchair or whatever it is now have at the top of the ramp, how can it now have 1,182 joules of potential energy? I thought it could only have 882.
Because if you were
Yeah,
to
but-
fall back down that ramp, you'd go a lot.
But so like you're trying to tell me that really, if you go up a ramp, you're going to slide down more than if you just fell?
Some of it goes to heat.
There you go. Where does the extra energy go? Goes into heat. Okay?
So if we
Goes
were
into
to
heat.
So
fall,
let's say this question came up, and it was laid on the steps like this.
Yeah?
Would we still be able, or not in the steps like this, would we still be able to answer it with just the lifting part if we wanted to skip the up?
No, because you'd have to recognize there was friction. Right?
I recognize.
You're going back to Beth's question. Could we do this like this? Not if there was friction, because you have to account for that. Yes.
We'd have to.
Yeah. Okay, does that make sense? Okay, I think that is all. I'm not going to spend a lot of time on this. This basically just tells you everything that I've done. I think this was provided to me by some person at one point, and I thought kids should have that. And I used to go through it. The only time I've ever really gone through it is because I like to mock myself here. This is a picture of me carrying a briefcase. See the guy here with no hair?
uh-huh.
And for some reason, I'm carrying a briefcase out like this. I'm not really sure what's going on there.
Well, as long as it's not
No,
all.
less work. Why less? Because how much work is done when I carry a briefcase from here?
No work,
No work at all. How come?
because you're not moving it up or
Same
down.
amount of. That's uninteresting. Okay, I'll be quiet. You guys have some. Oh no, I didn't hand them out. Right? I didn't hand out the actual question. Can you put the stack where it belongs? Just don't hit Riley or anyone else on the way.
Please no.
If you haven't hit someone, hit Riley.
Yes.
I want to write the exam.